Our question today comes from the 2018 paper, the higher tier, and question 7. And this one touches on some of the same things that we've had previously, but then also starts to do a bond energy calculation, which is why I wanted to do this one. The stuff at the start is stuff that we have also covered in a previous question of the day, but still worth going over. So chlorine is more reactive than iodine. I would start to explain that now, but that's, if those looking ahead you can see that's what question B is. It says, name the products formed when chlorine solution reacts with potassium iodide. Now chlorine is more reactive, so we get a displacement reaction, where a more reactive substance replaces a less reactive substance. So that chlorine will come in and kick out that iodine. It's kind of like when Indiana Jones tries to nick that golden statue, and he takes that bag of sand and replaces it to get out that statue. So it's simply potassium chloride. Now it's important that we remember that when halogens have reacted, they turn to ide rather than ene, and that will be very specific in the reaction. It says products. So remember, once we've replaced it, that iodide is going to come back out as elemental iodine. Explain why chlorine is more reactive than iodine. So this comes down to our atomic properties and trends on the periodic table. Chlorine is in period 3. That means it has got, its outer electrons are 3 shells away from the nucleus. And remember that electrons are negative and the nucleus is positive. So that's what's attracting it in. If I look at iodine, iodine's 1 period below, that's period 4. And therefore, 1, 2, 3, 4. Okay, oh, look at that massive, exaggerated 4th shell. Chlorine and iodine are halogens, and the way that they react is they want to gain an electron to make a full outer shell. So they want to gain an electron. And if I want to gain an electron, I want to attract it to my nucleus. Okay, it's kind of like, you can imagine, like those nuclei are like those people who stand outside of shops and go, oh, come into my shop, right? If you're really close by, it's really hard to avoid them and kind of not be tempted in. If you're the other side of the street, it's really hard. It'd be really crazy if they started walking over to like give you a leaflet and try and grab you into their shop. So the further away you are, the less you feel that attraction of the nucleus, and therefore the harder it is to gain that extra electron. So let's put that into words. Chlorine has 3 shells and is smaller than iodine. What does that mean? That means that the outer electrons are closer to the nucleus. That therefore means that those actual electrons are going to be attracted more strongly. Finally, to kind of wrap that all in together, that means it can gain an electron more easily. Moving on to the next one. Chlorine reacts with hydrogen to form hydrogen chloride. Explain why hydrogen chloride is a gas at room temperature. Answer in terms of structure and bonding. So let's think about it. Hydrogen, non-metal. Chlorine, non-metal. So because they're both non-metals, that means that we've got a covalent system of bonding. Now, because we have made a nice molecule, HCl, actually if I did a dots and cross diagram, look like that, everything is happy. If I have one hydrogen chloride, bond there, quite nice and strong, it's a covalent bond. But if I look at our lumps closer, and again we revised this in yesterday's one about diamond, we've got our weak intermolecular forces. They're easily overcome and therefore is a gas at room temperature. So let's put that together. Hydrogen chloride does covalent bonding and has a simple molecular structure. Our simple molecular structure has weak intermolecular forces between the molecules, and crucially, this doesn't take a lot of energy to overcome and break. Oh, let's keep the alternating pattern going, shall we? So that's a gas. Excellent, nothing particularly new there. But that leads us on to the next question. Bromine reacts with methane in sunlight. The diagram below shows the displayed formula for the reaction of bromine with methane, and we've got a nice displayed formula here. The table shows the bond energies and the overall energy change of the reaction. We've got some bond energies. Calculate bond energy X for the CBr bond. Right, so the first thing that I like to do on this question is I take a pen. You can use the fat side well, pretty much the first time, and I'm going to draw a line right through the middle of the entire question. Okay, and the reason for that is I want us to think and focus on the products, on the reactants and the products, and keep them separate, and then they kind of come together. First thing I want to do is calculate. Remember, when something reacts, we break all the bonds and then we make all the bonds. Or that's how we can calculate the overall energy change. I tend to think about this as like Lego. If you have a pot of Lego, some of it might be already built up from where you've previously played with it. So the first thing that you do is you break all the Lego pieces apart and then you put them together in a nice new way. And that's how we can end up with exothermic and endothermic. If I take a lot of energy to break them apart and I don't get much energy back by making, right? If I take a lot of energy to break apart the Lego bricks and the model I make is rubbish and I don't feel good about it, overall I've put in more effort than I've got back. It's an endothermic process of taking in energy overall. If I get more happiness or more energy out of making bonds than I do from breaking them, then I've overall got an exothermic reaction. And here, actually, where the energy has gone down, that means I've released more energy by making bonds than I have by breaking them. So this actually means it's an exothermic reaction. The way to remember the energy changes from bonding is bendomex. So breaking bonds is an endothermic process and making them is exothermic. Let's think about how much energy I have to put in to break these. So I always like to cross through my bonds and it just avoids silly mistakes. So I've got 1, 2, 3, 4 CH bonds, 4 CH. And I've got 1 Br. I can then look at my table. That's 4 times 4, 12. And if I stick that into a calculator, 1,648. I've got 1 Br bonds, that's 1 times 193. And that's 193. So overall, the amount of energy I have to put in to break them is going to be those added together, which is 1,755. So that is the amount of energy that I have to put in. Let's look at this side. I've got 1, 2, 3 CH bonds. So that's 3 times 4, 12, which is 1,236. I've got 1 CBr bond, and this I don't know, so that's 1 times X, that's X. And I've got 1 HBr bond. So that's 1 times 366. Now, I always like to cross them through because, especially on some complicated organic ones, people miss bonds. So I'm just going to do a last minute check. Yes, I've crossed through every bond. So let's add this up. We know that this side is therefore going to be 1,602 plus X. How are we going to put this together? Well, whenever we do these questions, we always do left minus right, because we are making bonds, that means that this number becomes negative. So it's always left minus right. So 1,841, this side, minus 1,602 plus X equals minus 51. I can then extract that brackets, putting the minuses in front. Then I can collapse these numbers together to be 239 minus X equals minus 51. Let's add X to both sides, plus 51 to both sides. So that means that X is 290 kilojoules per mole. Now you can see from my scribbles, and probably as I was following on that side, that you might have been glaring about that side being wrong. And again, that's a testament to the fact that you shouldn't be doing these in your head. Okay, I'm a teacher, I get things wrong in my head, even though my mental maths is pretty solid, not tonight. So use a calculator, okay? There's no such thing as a non-calculator science paper. But I want to show you this one because, again, this technique of looking at the left side and looking at the right side, I think unlocks these questions really nicely.